All this information I'm going to talk about today, I just released in a report that came out about 2 weeks ago and is on our website. So if you want more information on it beyond what I'm going to talk about today, you can find it there. So I'm not going to talk too much about the OESF because we've talked about it today, but I want you to understand that most of the forests are in the second growth conditions right now. When we look at we've had a gradient of management throughout the years within the OESF, some more extreme than others, and hopefully we're getting better with how we're managing things. But in the past, most of our streams, they cut right through the streams, and there weren't as many restrictions on roads. Like you can see here, the road goes right through the stream. Now, today's management, we mostly rely on buffers to protect our streams. And well, most of our harvests have gone on at different times. They've all been allowed to mostly recover through what we're going to call passive restoration, where these forests kind of develop on their own. We kind of talked about the HCP earlier, but it was developed in the 90s, and it kind of guides our management. It provides protections for spotted owl, marble murrelets, and salmonids. Now, within the HCP, there's a condition for riparian validation monitoring. That's kind of where I come into this whole picture here. And this monitoring is to evaluate the cause and effect relationships between DNR management, habitat, and salmonids. So we really want to find the links between our management, both our forest and stream habitat, and our fish. And we do this through monitoring about 50 streams. Most of them have been shown earlier. Now I want to emphasize that these are just kind of our smallest fish-bearing streams. We do monitor larger streams and adult reds, but I'm not really going to talk about that today. Now we also can't sample all these streams within 1 year. So I sample 20 of them annually, and then the remainder I split between even and odd years. Now, since we know most of the conditions are relatively the same within the OESF, we've added these 11 unharvested watersheds to create a diversity in conditions so we can understand more what should be going on within our systems. Now, when we selected these watersheds, they're picked by different means, but in general, we looked for watersheds that were over 100 years old. Now we're going to get into my analysis and what I did here. So the first thing I did was develop a conceptual model. Then I used the monitoring data to evaluate the model as well as the conditions on the OESF. And then we figured out what we saw, and then we made some ideas of what's going on with our monitoring and management. Nope. So the critter we're going to look at today are age 1 and older cutthroat. And the reason we're going to look at this guy is for 2 reasons. 1, it's the most commonly found species on the OESF. And 2, they spend over a year within our watershed, so they get really conditioned to our habitat. Now here's my model. There's a lot there, but we'll get through it. So there's 4 main components of this model that we're going to look at. 1 is in-stream cover. 1 is kind of our light food aspect, hydrology, and then the relationship between the fish's size and density within our streams. So we're going to start looking at the size-density relationship. So we know every stream has a capacity to hold a certain amount of fish. Now within that capacity, you can have a bunch of small fish, or just a few large fish, or some combination in between. So we want to see if this is really going on within our streams. So that's going to be the self-thinning aspect of our model. Next, we're going to look at in-stream cover. So fish use cover to avoid predation and things like that. And some of the more common forms of in-stream cover are wood and boulders. Now, this Penaluna et al. Paper in 2015 found that in-stream cover could actually be limited in a lot of our streams. So we want to see if this is going on within our streams. Now, all streams act a little bit different, and we have a diversity of streams. So in higher gradient, I'm assuming that fish are going to be more reliant on boulders. Now in lower gradients, they might be more reliant on in-stream wood. And the amount of in-stream wood is likely determined by our riparian trees and our tree size. The next thing we want to look at is our light food aspect. And a lot of this came about from these studies by Dana Warren and Matt Kaler that have looked at the effect of these second growth forests on our streams and how they kind of grow up very thick together. And this limits the amount of light that can come into the stream, which limits the production in the stream. So we get less macroinvertebrates and things like that, which will go and eventually cause less fish. We also know that canopy coverage is good for our water temperature, to keep our temperatures low. So we also wanted to include that in our model. And I also added this percent hardwood metric in our analysis. And that's just to see if more terrestrial inputs are having an effect on our fish. Third thing we looked at was hydrology and how stream depth was important for our fish. And stream depth could be controlled by many factors, watershed area being one, and the other was this, the amount of second growth within our watersheds. This was a paper that was done by Perry and Jones in 2016, and they found that these second growth forests actually suck more water out of the watersheds than old growth forests, and we wanted to see if we could see that effect within our forests. So here's, once again, our full model, and we'll come back to this several times throughout this talk, but I think it's a good mix of keeping things relatively simple, but having some needed complexity. Okay, so to evaluate the model, I used 4 different analyses. I used nonlinear quantile regressions to look at our self-thinning aspect. I used correlations to look at the relationship between our habitat and our capacity in our streams. This didn't really follow the path of the model, but just see the importance of each of our metrics within our model. I did a watershed comparison to see what's going on in our higher capacity watersheds to our lower capacity watersheds. And then I used a model selection approach to see if we could kind of rank which habitat metrics may be the most important. So here's our self-thinning analysis, and here on our Y we have our fish per meter squared, and our X we have our average fish body size. And we ran 5 different quantile regressions. And this is to see how watersheds are different, basically. What we can see as we got more and more capacity within our streams, we had more of a self-thinning relationship. Now in our lower 2 quantiles, the 10th and 25th, we don't have a self-thinning relationship. So here it's likely that habitat conditions are low enough that the fish can't express their full life history within these watersheds. Now, I really like this graph because I think this is a good understanding of our current status of all of our watersheds. And I'm hoping that in future years when I get more and more data, I can see, are we getting more fish that are going to the self-thinning relationship and getting these higher capacities? Or are we having fewer fish and are being more restricted in our kind of our 10th and 25th quantiles? So we'll see how that develops over time. So when we go back to our model, self-thinning seems to be an important aspect within our watersheds. So that's something we really need to watch in the future. So now we're going to go to our correlations, where we looked at all the habitat metrics within our model and compared them to a metric we developed on capacity based on our self-thinning. And what we see here, that our percent second growth had a negative relationship with capacity, gradient had a positive relationship, temperature had a negative relationship, percent boulders had a positive relationship, and water depth had a positive relationship. So what does this mean? Let's go to our model. Now if we look here, higher gradient streams are doing good. Streams with lots of boulders are doing pretty good. Lower water temperature streams are doing good. Streams with more depth are doing good. And with lower amounts of second growth forests are doing pretty good. Now we're going to go to our watershed comparison. And here we're looking at just the highest capacity streams, so watersheds that were above our 75th quantile, and then our lower capacity streams, so below our 25th quantile. So, and what we found here is that, once again, higher gradient streams had higher capacities. Deeper streams had higher capacities. Streams with lower water temperatures had higher capacities. Higher percent boulders had higher capacities, and in-stream wood came into play here and was higher in our higher capacity watersheds compared to our lower capacity watersheds. And then percent second growth, watershed area, and canopy closure, there was no significant difference between these metrics. So we'll come back to our model. This kind of gives us support for both in-stream wood and boulders within our in-stream cover model. Lower water temperatures were once again, so canopy coverage are doing a pretty good job with our temperatures. Deeper streams, and then watershed area and percent second growth didn't really show up within this analysis. Now we're going to do our model selection technique. Now, I couldn't use all of the metrics within our model because we only have about 60 watersheds here. So I limited our analysis to about 6 important metrics here, looking at canopy coverage, stream depth, percent second growth, percent boulders, gradient wood. And with this approach, I built a bunch of different models using a combination of all these different metrics, and then we ranked them based on their AIC score. Any AIC, any model that had a score within 2 units of the top model, we've determined to be significant, and those are the models we're going to kind of concentrate on here. So we had 6 models that ended up being within 2 AIC units of the top model. What you see here, the only metric that showed up in every model was depth. So stream depth is probably our most important factor for determining capacity within our streams. Next, we're followed by gradient, which kind of supports what we found in our other analysis, that these higher gradient streams are doing pretty good. And they seem to be important when you're determining capacity. Boulders came out pretty important. Canopy came in, you know, we got some support for that in our last model down there. And wood, we didn't get any support for within this analysis. So that was interesting. So we'll just come back to our model, higher gradient streams, lots of boulders are doing pretty well. Stream depth is probably the most important factor going on in our streams right now. Percent second growth got some support there, and then canopy had very minimal support, but more than in-stream wood. So here we bring everything together, and once again, you know, this model tells us some of what we've seen here. Stream depth's important, lower water temperatures. High gradient streams doing pretty good, boulders doing good. But what I found most interesting, so why aren't some of the things coming out that are important in our literature? So why isn't canopy coverage important here? In-stream wood, there's been a lot of research on in-stream wood and the importance of in-stream wood. So why is that not important within our model? So I kind of looked into the data and looked a little further on some of these things. So my first thought, well, maybe cutthroat just prefer higher streams, higher gradient streams. But when I really looked in the literature, that didn't seem to be the case everywhere. Like in this Rosenfeld and all paper in 2000, cutthroat densities were actually highest in these lower gradient streams. So we may have something going on different here than on other streams. And what I think may be happening is, I don't think in our sample at least, we have enough lower gradient streams with high amounts and volumes of wood to really show the importance of wood within our analysis. And there's a little support from this in this, the poster that I presented earlier, where we found we have reduced amounts of wood when we compare to this Gret study of 1985. So this probably needs to be looked in a little bit more on the importance of wood in our lower gradient streams. What this does mean, or could mean anyways, is if in-stream covering is limiting production of salmonids, our higher gradient streams may recover quicker than our lower gradient streams. Next, I wanted to see what's going on with light and our food pathway here. Now, if you look at our canopy coverage range up here, it's very narrow, from 83 to 95%. And then I looked at the median of all the watersheds within the OESF, and it was about 92%. And we added all these unharvested watersheds so we have this better range of conditions. But if you look at this, we still have a 92% canopy coverage in our unharvested watershed. So I went back into our data, or into the literature a little bit, in this Kaler and Warren study, and I realized in their old growth systems they had about a 77% canopy coverage in these systems. There's another study that was done on the park, the nearby national park here, and they also found around 77% canopy coverage in their old growth systems. So what I think happened here is when we select our watershed, we use this 100-year criteria for selecting these watersheds. So I think we have an uneven portion of more mature forests rather than old growth forests. And this kind of gives you a timeline of how long it may take for some of these streams to recover in these lower gradient systems, where you need that influx of wood and this canopy cover to open up. The next thing I wanted to look at was that Riparian Jones paper, where this showing that these second growth forests suck up more water than these old growth forests. And you know, through my analysis, actually there's a lot of support for second growth, and there's a lot of support for stream depth. But there is no relationship between our second growth and stream depth. So what I think is going on here, I think percent second growth is actually acting as a metric for disturbance within our watersheds more than the age of the forest in general. So this is something, if we really want to look at and explore more, we may need to use more of an experimental approach to see if it's really taking up that much water. So we've now gone through about 20 years of recovery, at least 20 years of recovery. And these are kind of my areas of concern. So one are lower gradient streams and potentially in-stream wood, high levels of canopy shading throughout the forest, and watersheds with lower water depths. And so climate change makes me a little more nervous about this water depth thing, because we'll expect kind of more extreme lower flows in the summer, and that could be very detrimental to our fish. So management implications. So growing riparian forests with buffers takes a very long time. And if we want to speed up salmon recovery, active restoration may be something we should look at a little bit more. So I would recommend that we start conducting more experiments using riparian thinning that includes with and without tree tipping. Because some of the things we need to consider are how feasible is this with our management? Wood recruitment. So if you thin without putting trees in the stream, you will actually reduce the recruitment of wood into the stream. So you could actually create worse conditions, in theory anyways. Now, if we do mess with the canopy, we also got to be very careful with our water temperatures. We've seen in the past that we've gotten really high water temperatures through past management. So something we need to think about. Canopy coverage is obviously, because that's going to be the main treatment, and salmonids. So finally, our monitoring implications. When I looked at our distribution of samples, what I really noticed was from about 11 to 40% of the forest in old growth, we don't have a lot of watersheds within this condition. And my guess is there aren't watersheds in this condition across the forest, so we don't know the importance of these watersheds without having them within our sample. My other thing is that I think we're missing an old growth component within our sample, and we need to be careful of that when we make conclusions, because that could lead to false results. And then finally, it may be a good time to start experimenting. And with that, I will take any questions and like to know all the people who have helped me out with this.